Very good evening to everyone present here, especially Pragya ma'am, Jeevan sir, Meenakshi ma'am, and all dignitaries and my very dear participants. So I warmly welcome you all to the fourth day of our workshop. It is a pleasure to have you all here as we continue this enriching journey of learning and exploration. Before we begin today's session, let us briefly reflect on day three. Yesterday's session was truly engaging and intellectually stimulating. Mr. Jeevan Pandey beautifully demonstrated how simple physical systems can reveal deeper insights when analyzed carefully. The discussions encouraged us to question our assumptions and interactive approach kept all participants actively involved. It was wonderful to see such enthusiastic participation and thoughtful questions from everyone. Today, we are once again privileged to have with us our esteemed resource person, Mr. Jeevan Pandey, an experienced and inspiring physics mentor. His deep insights and engaging teaching style continue to guide us throughout this workshop. The theme for today is very thought-provoking, that is a multi-body constraints. Who really controls motion? Through today's session, we will explore some fundamental yet fascinating questions. Do forces truly decide motion, or do constraints play the dominant role? The other one is friction merely resisting motion, or is it actually enabling it? Then we will explore what surprising phenomena emerge when motion is restricted. So I am confident and very sure that today's discussion will challenge our usual perspectives and deepen our understanding of motion in a complex systems. Let's stay curious, participate actively, and make the most of this insightful session. Now I invite Mr. Jeevan Pandey to please take the session forward.
Thank you, ma'am. Once again, good afternoon to one and all. We are 10 minutes past 5:30, but I promise I'll be leaving by 7:30. I understand that all the participants must be feeling tired because everyone is busy in their own set of works. So by the time we come home, we return from the office to back to our home, instead of relaxing, we are sitting in front of our laptops, thinking about some insightful questions. But that's the fun. And today is the fourth day of, we have completed half of this journey of this particular workshop. Today is fourth day, third day and fourth day. Third day, we devoted most of the discussion to the concepts based on rotational effects, torque, angular momentum, rolling. So most of the ideas that we discussed yesterday was centered around symmetry, angular momentum, and rolling. Today, as was introduced in the introductory version by Madam, so constraint and the role of constraints in multi-body systems, multi-body constraints, this is the topic given to me. And I hope, like yesterday, of you will be interacting well. But once again, yesterday also I requested. Today also, at some points of discussion, we will need really sincere attention from all of us. So let's see where our discussion leads us today. So let me first share my screen, and let's start from a very simple example. Simplest of all, the cute little Atwood machine. Before I start, may I know if the screen is visible?
Yes, sir.
Okay. Now this figure is very common, and that was the reason of choosing this particular figure. So every plus two going child draws this figure, draws the free body diagram, and Here we have a set of masses M1 and M2, as you can see in the figure. They are tied to a light string, massless string, and that string passes over a pulley. The pulley has been represented as ABC, and the pulley's center of mass is fixed by means of some pivot or support, which is represented in the figure. And we know that if the system is released from rest, here we assume that the mass M2 is greater, suppose. Let me make this M2 as greater than mass M1. Now here the first question, which will be a very simple one at the first glance, goes like this. The forces that are to be included in the free body diagram. Whose free body diagram? Of the pulley are. Now some options are given here. Tensions by the hanging portions of the string, weight of the pulley, reaction force by the axle, normal reaction by curved part of the wrapped string, and frictional force by the curved part of the wrapped string. Generally, the free body diagram which we see in the textbooks, which we discuss in the class, based on that, or based on whatever comes to your mind, try to put up your opinions in the chat box. Then we'll start our discussion. By then, some participants are also expected to join. Which forces are to be included in the free body diagram of this pulley? Those who have recently joined, let me tell, we have to indicate the correct options in this particular question, wherein you are supposed to think about the forces which are to be included while drawing the free body diagram of the pulley, only the pulley. I request everybody to kindly respond in the chat. We are getting some responses, I hope.
Yes, sir, we are getting A, B, C, B, C, D, E, B, C, D, E, B, C, D, E, A, and D.
And of course, I forgot to tell, more than one options are certainly expected in this question.
Yes.
So far, I feel only 50% of responses have been received. I
Yes,
request.
sir. And there are multiple, many of they are writing B, C, D, E collectively. Otherwise, there is option A, B, C, A, B, D, E, B, C, D, E. बी सी डी ई मैक्सिमम ने लिखा है जो है इसमें. अदरवाइज ए बी सी ई ऑप्शन भी है, अकेला ए बी सी भी है, और एक ने ए बी सी डी ई पांचों लिखे हैं. सो इट्स लाइक दिस.
Okay.
हाँ जी.
I'll just wait for one more minute.
हाँ जी.
Okay. Now let me start today's discussion with this simple Atwood's machine. Here we have to represent the forces acting on the pulley. In the diagram itself, I can represent. When we talk of the pulley, certainly most of you have chosen multiple questions. And I think among all the options, B is always present. When we are
Yes.
talking of the weight of the pulley, it must be included and it will be acting in downward direction. So let us call it as W. It's okay. Then reaction force by axle also most of you and almost I think everybody has chosen. So the reaction force by the axle connected to the pulley at the center, it is expected to be in upward direction. D and E also many responses we have received. Normal reaction as well as frictional force by the curved part of the wrapped string in contact with the pulley. Now this figure which I have done on the right side, this represents the string.
Yes.
And this string is above the pulley. Of course, they are in contact, but just to make it clear, I am representing them as separate objects. Since they are in contact, certainly the string must be rubbing against the pulley in some direction. Now here I have written M2 is greater than M1. So it is expected that mass M2 should accelerate downward and mass M1 should accelerate upward. So relative to the pulley, this string is expected to turn in this sense. Sorry, relative to the ground. The pulley and the string remains relatively at rest because we assume that the pulley is rough. Pulley is rough means the surface between the string and the pulley is rough. So that when string tries to slide over the pulley, there is friction on the string in opposite direction. So friction on the string will be in this direction. And friction on the pulley at different segments will be like so. At different contact points will have different directions of friction, but there will be some frictional force. Yes, frictional force by the curved part of wrapped string must be included in the free body diagram. Let us not bother about the direction of the net frictional force. There will be some frictional force which I write as F. And of course, because this string is pressing against the pulley, so over here the pulley will be pressed like so, over pressed like so here, like so. It is being pressed by the string radially inward. And that will result in, their vector sum will result in net normal reaction. So normal reaction will be there, option D. Frictional force by the string wrapped on the pulley, that will be there. Reaction force by the axle will be there. Weight of the pulley will be there. All of you must be agreeing with this. And I don't think there is much discussion needed in these 4 points. Now the first part, which we draw the most, we have received some answers wherein A is not included. Tensions by the hanging portions of the string connected to the masses on either side. Now the curved part of the string is like this. And the hanging part of the string, to the left side it is like so, and to the right side it is like so. The entire string is 1. So this is A, this is B, this is C. This part of the string, we draw the figure like so, that here there is a mass M1. So there is some tension in this part of the string. So this tension, let me call it as T1. Right side of the right hanging part of the string, let us assume the tension to be T2. Now two possibilities are there. Now try to figure it out. The tension T1 over here. This tension T1 is acting on the string, point A of the string, or it is acting on the pulley. What do you think? In the strict sense.
String, sir.
String.
String. Okay. All of you agree with that?
Yes, sir.
What about the other side? This tension T2 at the other end near point C is acted by whom? By this part of the string. On whom? At point C, which is a part of the string, not the pulley. So just as at point A, T1 is acting, likewise at point C, T2 is acting. Both these tensions are acting at points A and C, which form part of the string. They do not form part of the pulley. So in the strict sense, when we talk of the free body diagram of this pulley, then we should include mg, that means weight of the pulley. We should include reaction of the axle. We should include the frictional force exerted by the curved part of the string over here. We should include the normal reaction by the curved part of the string over here. But we should not include T1 and T2. We should not include. But we do include. And we get the answer also. So in this discussion, today's discussion, we'll be having a discussion circling around these particular concepts. And slowly we will discover and we'll try to see why we show forces T1 and T2. If somebody shows forces T1 and T2 on the pulley, like so, is it wrong? Is it right? If it is not correct, then why do we get the answer? And we solve the numericals. Every books we find this figure. So our discussion will be based on that. If the members permit me, so I would like to proceed further. If there is nothing, no query in this part.
Sir,
So what is the basic? Yes, ma'am.
if this is as you free body diagram, you have drawn the normal force by the pulley on the string is equally in all in from where the string is touched the pulley, but at the point A and C where the string is free from the pulley, so at point C, the tension in the both the points will be same for the only the string, because masses are at the end is different here. That is my question. If I'm
Madam, could you please once again repeat your question?
this is in the free body diagram. You have drawn the weight of the pulley is acting downwards and the reaction force is upwards, right? And
Okay.
the string around it, you are doing the frictional force in the direction, in which direction frictional force is acting. In
That
the
we will discuss. That we have not yet discussed.
right. So if I'm not discussing that point now, but what is the tension by the free string, which is not attached at the point A in the right hand side diagram, extreme right, and at C, is the tension is at A and C only for the string at that points are same or different?
Madam, are you asking me whether T1 and T2 are equal or not? Are you asking this?
This thing at the point when it is not touching the pulley.
That will, of course, that is a part of the question in the today's discussion. And whether or not
Actually,
they will be equal.
I'm late. You joined late. Sorry, I am for extremely sorry.
No, it is a part. It will be forming a main part of our discussion. And under what conditions they will be same, or under what conditions they will not be same, in details
Right.
we'll be having our discussion in the
Thank
today's
you.
webinar.
Thank
So let us now proceed with this much idea. What is the basic key takeaway? Strict sense, if you draw the free body diagram, we should not include the tensions by the hanging parts of the string. Other B, C, D, E, there is no doubt. Madam, just now you are asking this question, and here it is.
Oh, yeah. That's right. Thank you, sir.
Consider.
Yeah. Let
We'll
me have
discuss this.
patience. Let me have patience, sir.
So consider the curved part ABC of the string in contact with the pulley, as Sutapa ma'am was saying. If the string be light, now I have marked a condition here. If the string be light, that means we are assuming its mass to be 0. Whose mass? String's mass to be 0. And inextensible. Then, now here we have three options. Tension at each point on this portion. Which portion? On the curved part ABC. Wherever the string makes contact with the pulley, I am talking only about that portion. So will the tension at each point be same? The point B, whether the tension gradually increases from point A to C or decreases from point A to C. I request everyone to kindly ponder about this and put their thoughts in the chat box. No hurries, please take your time. Note that the string is light. And one more thing I should say, that between string and the pulley, the surface of the pulley in contact with the string, that is rough. That we have to assume. Otherwise, the pulley will not roll with the strings. So this surface we have to assume rough. And the string is light. I request everyone to do participate in this response giving part. We'll wait for 1 more minute, then we'll continue our discussion. Okay. Would somebody help me in
Sir,
knowing what?
it's equal number almost for the options A and B.
Okay. Options A and B.
Yes. Almost the
And
same.
nobody is
number.
writing for C.
No one has written C.
Okay. Okay. Now, may I know what is the reason for option A? Tension at each point on this portion of the string has the same magnitude. Would somebody volunteer to reason this out?
I think, sir, the string is not stretched here. It can't be extend. So the tension in the string is same everywhere. It is inextensible. That's why, and light also.
Light also. Inextensible, of course. It is light. So why light? If a string is light, why do we say tension at all points should be same?
Because it is light, so there is no weight. I
Okay.
think so. So there is no reaction
Good.
force.
Yes. Okay, madam. I got your point. Generally, we discuss such situations that if we have a light string, before discussing that particular problem, let us come to this. Suppose this string is light. Then why at two different points, say A and B, tensions be same? In fact, in this case, tensions at points A and B are equal. Why do we say equal? Let us consider this part AB of the string as the system. If this part AB is the system, let me redraw this. Then at point A and at point B, this is the system, we have to indicate the forces. So by the lower part of the string, that is exerting a force TB, tension at point B, and the upper part of the string is pulling it up. So that we'll call it as TA. And this part of the string being light, we assume its mass to be 0. Since it is at rest, even if it is accelerating, no, not only light, if we have this situation also, here of course they are equal. Let me talk of another situation wherein for both the cases we'll have similar discussion. This block is there, this string is there, similar points A and B we can have, and suppose it is accelerating towards right with acceleration A. Somebody is pulling this string like so. So here the free body diagram will be something like this. A and B are there. So here we have tension TB, here we have tension TA, and this part of the string which we assume to have 0 mass, it has a finite acceleration, say A. Then we write TB minus TA is equal to mass times acceleration, but that mass is 0, that's why this happens to be 0. and that's why we write TB is equal to TA for light string. If the string were heavy, then M will not be 0. In that case, TB minus TA in the upper figure will be some mass of that part of the string AB times acceleration. So here we will find that TB is greater than TA. So that I hope the logic behind your argument was this, that if we have light string, its mass is going to be 0. So if its mass is 0, whatever be the acceleration of that part, net force has to be 0, and that's why the tension on either part of the strings must be same. That logic is correct, 100% correct. But in addition, there is something else which is happening here. Let us try to choose a segment of string in our original figure, this segment, this part. And let us draw this free body diagram of this part. For the sake of clarity, I have represented it very big, but this part you should assume it is an infinitesimal small part. Let me call this part as P, this point as P, this point as Q. Along the tangent, we can expect the tension here, that is TQ, and at point P along the tangent, there will be tension TP. In addition to TP and TQ, is there any other force on this segment PQ of the string?
Yes, sir.
Normal reaction.
In normal reaction and attached with the, which is part is attached with the pulley.
Okay. Let me call that part of normal reaction as DN. And who is exerting this DN? It is being exerted by that part of the pulley which is in contact with the segment
Right.
PQ of the wire. Okay. Who is exerting TQ? The other part of the string below point Q, and likewise TP. Any other force?
So friction.
Friction, sir.
Friction. By whom?
By
Due to the
By the contact surface of the pulley. In which
Yes.
direction?
Downward.
Sir, you are
See,
considering
relative to
the.
the pulley, this mass
Hmm, hmm.
this part of the string is trying to go down. So relative to pulley, it is going in this direction. So the friction should be in opposite direction. So one more force will be there, that is frictional force, which I call as suppose DFS. This is static friction between the pulley and the string.
So can we think
Now
of
let
it
us okay.
so like if a pulley is going
Sir, please
downward,
respond.
if pulley is going downward, then it will try to take the string also downward to reduce the relative motion between the string and the pulley.
See, between the pulley and the string, there is no relative motion, but the string tends to slip over the pulley. It tends to slip, but actually there is no actual slipping. We are assuming that case wherein the friction between the pulley and the string makes the pulley turn. So in this case, on the string, the friction should be in this direction, DFS. And on the pulley, the friction should be in opposite direction. Same action and reaction pair, DFS. And it is this friction which makes the pulley turn like so, about point O. That's why the pulley turns. The pulley turns because of the frictional force between the thread and the pulley. Had there been no friction, the pulley will not turn. The torque to turn the pulley is provided by the frictional force. What you are showing, sir, saying is basically the relative motion between pulley and string is not there because there is sufficient friction, and that friction is causing the pulley to turn. Here we are talking about the string, so the frictional force DFS will be in opposite direction on this string, which I have represented here also. Now, along the length of this part PQ of this string, this DN you can see it is perpendicular to the length PQ. We can assume it to be perpendicular. So along the length, if you see the forces, this side we have two forces. one is tension at point P and DFS, they are tangential and in same direction. And this side we have another force that is tension at point Q. And they should balance each other because we have assumed that the mass of the string is negligible. Had the
Sir,
string, yes
सर
ma'am.
यहाँ पे आपने ऊपर तो आपने डीएफएस दिया, नीचे भी तो आप इधर के तरफ राइट हैंड साइड पे जहाँ पुली टर्न कर रहा है, दिस साइड आल्सो यू आर टेकिंग डीएफएस एंड देयर यू आर टेकिंग द एक्शन एंड रिएक्शंस आर cancel out because it is a same force and acting in the two different bodies. So why TQ के साथ DFS नहीं आ रहा है, इधर DFS आ रहा है if it is a cancelling out?
Let me make it very clear, madam. This lower one, DFS, is on pulley.
Right.
The upper one is on
String.
string.
Hmm.
Now, whose
Action and
free body
reaction.
diagram we have drawn here? This
Uh,
PQ represents the string.
hmm. Hmm.
On string, we are drawing the free body diagram. We are drawing the FBD of string. So,
Okay.
string, the lower DFS, which was there in the earlier figure, this is on the pulley. So,
Hmm.
this should not be shown in this part.
Right. Thank you.
So, let me omit that to avoid confusion. So, TP plus DFS minus TQ, this will be mass times acceleration. And that mass is 0. That's why this becomes 0. And this suggests that TP plus some frictional force is equal to T at Q. That means my TQ is something more than TP. That means tension at point Q is greater than tension at point P. Now you can see where is point P, where is point Q. Q is this side, this is Q, and this is point P. So tension at point Q is greater. So likewise, if I choose two more points R and S, exactly on similar analogy, we can say that tension at S is greater than tension at point R. And the same reasoning will be applied for all different segments which you can think of on the part of the string. And if we combine this, we'll find that in this part of the string, starting from A, the tension goes on increasing gradually, continuously, till we reach point
From
C.
A to C.
From A to C, gradually the tension rises beyond point C. If the string is light, or at all the points, tension will remain same. Beyond point C and beyond point A, the tension remains TC, 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 and here it remains TA, TA, TA. Why? Because this part of the string, we don't have any friction and we don't have any mass. So what is the key takeaway? Based on this discussion, our key takeaway is that if we have any sort of string in some sort of motion, if it is light and if there is no friction, these two conditions should be satisfied. Under these two conditions, tension will remain same at each and every point of the string. If either of these two conditions fails, either the string is heavy or there is some friction, in such cases there might be a situation where the tension may not remain same everywhere along the length of the string. So in this particular example, the tension will gradually increase from point A to C. I hope now we are in a position to move further.
Sir, one small submission with respect to this.
Ji sir.
Considering light strings only, suppose length of the string is 2 meter and it is hanging vertically, and there is a person who is hanging on that string at 1 meter.
Okay, sir.
So in that event, I think some section of massless string will have non-zero tension, some would have zero tension. So is it to be considered under this scenario only?
So let me try to understand what you have asked. So there is a string or a rope which is hanging from
Yes,
some sea.
massless. Yes.
This rope is massless.
Yes, sir.
Okay, it is light. So
Huh.
let me put it together. Then there is some point somewhere in the middle where
Where,
somebody is hanging
yes, sir. In equilibrium.
and he is also at,
Equilibrium, sir. Huh, correct, sir.
okay, just,
So
uh,
can we say that upper part and lower part, although they are part of same massless string, one part has non-zero tension, other has zero tension?
okay. I will give you a 5 star, sir, for helping me out. What you are saying is exactly correct. Of course, the upper part will have a tension which is equal to weight of the person, but in the lower part, the tension, because below that there is no load, so the
Correct.
lower part is expected to have zero weight. So yes, different situations can arise. So yes, this example is correct. And probably you wanted to emphasize on the fact that whatever two conditions I have cited, other than that also you have thought of a situation wherein tension at upper half and tension at lower half are different. Thank you, sir.
So my question is, sir, should this be considered as one single string or as fragments? Is there any definition as per your knowledge, sir? Because to me it looks like one string only. So that was my submission, sir.
Of course, there should not be any confusion regarding calling it as a single string or not. Of course, it is a single string only. But this single string, we have put it into such a situation wherein its one half or a portion of it is being subjected to a downward force, being exerted by the weight of the person, and its other half of the same string is left free to hang. So we cannot call it as two part, but of course the different parts are under different situations that we can say.
Okay, sir. Okay. Thank you,
Okay.
sir. Thank you.
Or if it is not light string, then that is it, the conclusion is valid. Suppose the lies but the example is given by the person. If the
Yes, sir.
string
In
is
that
not
case,
light, T is not
please,
zero, right? If suppose if it is not light, then the lower part still have a tension, right?
yes, and that tension will be different at different points.
Yeah,
You are
yes,
correct,
yes,
sir.
that's
Yes,
what.
yes, sir.
Yeah, that's the
That
most real
see,
case.
tension at any point will be equal to entire load which is below that. At any point, the tension which you are willing to find, that will be equal to the load of all the things which are below that point. If the string is having some mass, its weight will come into play. And that's why for a heavy rope, tensions at different points will be different. It will be zero at the lowest point. Here TC will be zero, and it will be maximum at the highest point. TA will be maximum.
So this is the most
So
real cases, right? This is the most real case.
yes, physically this is the acceptable case.
Real case. Yeah.
We are assuming, that's why we have to specify in numericals that assume the string to be massless, light. We are assuming that. But in actual, we cannot have massless strings. So in physical situations, certainly there has to be a gradation in the tension. Yes, sir.
Sir,
Sir, what
one more insight for this particular situation in which a person is hanging over the string. What is the actual? No, not sir. That person problem. In our earlier cases, mg was responsible for tension, but for this hanging person, I want to ask the question to forum. Basically, what is responsible for the tension? Whether it is weight of person or something else.
It is actually
The person.
it is the friction between the person and the string, but it is equal to weight of that person. So indirectly, it is related to weight, but if you in the strict sense you are asking, it is not the weight of the person, it is the friction between his palm and the rope.
Sir, in
Because if
addition, yes, as you said is correct. But in addition that upper portion also has some weight. So obviously, the tension in the upper portion is due to the, as you said, is the friction given by the friction between the person and the string where he touches, plus the weight of the upper portion, some small portion, right?
completely agree with you, sir. Yes, sir. Total weight. Here W you should
Yes.
write as weight of the string
plus
plus
that person.
person. Yes, sir. Basu sir, should we proceed? Or you wish to add something? Okay.
Sir, excuse me. Generally, at the 11th and 12th level, when we are talking massless and light strings, we take, when you're saying TQ is greater than TP in the slide that you presented right now, we usually equate it to the inequality of masses, no, directly?
Inequality of masses.
Yeah, because you said M2 is greater than M1. So from there, directly, can't we conclude that TQ is greater than TP?
No.
Because the weights will automatically reflect on the tension, no?
No. If I'll just erase this. If I've understood your question, basically you are asking that if we have the part of the pulley like this, see, if there is no friction between them, between the pulley and the string, if there is no friction, then one thing is for sure that pulley will not rotate. For pulley, the angular velocity, the angular acceleration will be 0. In that case, the tension in both segments of the string, here I wrote TA, I think. TA and here TC. Both TA and TC will be equal.
Isn't that
Even if the
equation more
masses,
related to the masses, sir?
how are they related to the masses, ma'am? Are they equal to the masses?
No, because that is the counter reaction to the weight, no?
That is the counter reaction to the weight when the mass is at rest. If I have a string, if I have a mass, say M1, then here I'll write that tension is equal to M1G. But imagine that string tied to the same mass M1, just I'm giving a physical situation, but the other end of the string, suppose it is not tied to any support, and I allow it to fall. With some, thank you, madam, for asking a very good question, and that will help us all. Can we say here tension in the string is equal to M1G?
No, it's not.
In fact, if it is in free fall, so basically what should be the equation? The equation will be this is T and this is M1G. So here we'll write the equation M1G minus T, that is the net force, and that is equal to mass M1 times acceleration. So here A will come into picture. And in this situation, when the masses are different, the masses will accelerate. And if you remember, madam, in chapter, I think, when we don't talk of massive pulley, when we talk of light pulley, don't we draw the figure like this, M1, then M2, then here we write M2G, here we write M1G, and we draw tensions to be equal both sides, T and T, and then we make its acceleration downward. M1's acceleration, we draw it as upward, and then we write the equations for M1 and M2. So when we have not discussed rotation and when we have assumed the pulley to be light, there we take the tensions to be equal. Why are the tensions equal here? We have to assume that there is no friction and the string is light and inextensible. Under such situations, the tension will be equal. The pulley we are assuming massless. But here in this situation, we are considering rotational effect of the pulley. We are talking about its moment of inertia, mass. In this case, there is some friction between the string and the pulley. Here, in such situation, the tensions at the two parts of the string will be different.
Okay, got it, sir. Yeah. Thank you.
Okay. Let F be the, so far we have discussed about tension on the string. Now let's shift our focus to the friction part. Let F be the net friction on the pulley by the string. Which part of the string? The part of the string which is in contact with the pulley. Think about it. Let me cut this A. So there is no A here. So you have to identify the the direction of the net frictional force on the pulley by the string, whether it is upward, left, or right. So I'd pause here for a couple of minutes. I'd request everybody to put their opinions in the chat box. Here, of course, you should remember M2 is greater than M1.
Yes, sir.
In all our figures,
M2 is greater than M1. Okay.
Okay, ma'am, could you help me in
Yes,
knowing the
sir.
responses?
Sir, number one पे D है, most of the choices. Then second is B, and one has a written this C also, C. So
Okay.
B और D main है, एक ने C भी लिखा है. 2, 3 have written C.
Okay. That means most of the
B, C.
responses are option B.
No, most are D. Number one D, then second is B, and third is C.
Okay.
Yes.
So this is the sequence.
Yes.
Okay. Thank you, ma'am. So briefly, I'll discuss it. I think most of you have chosen option number D. So it indicates
Yes.
that it did not be discussed much. Let us divide this upper part of the pulley into different segments. These segments are in contact with the curved part of the string. The string I am not drawing here. Now the pulley, as I have shown here by alpha, it has tendency to slip in this direction. Not slip, it is rolling in this direction. Who makes it roll? We know frictional force. So on this segment, the first segment which I have drawn here, the frictional force will be tangential. Let me call it as dF1 vector. And who is exerting that frictional force? It is being exerted by that part of the string which is in contact with this much part of the pulley. Likewise, over here in this segment, this part, the friction will be in this direction by the string. Here in this part, the friction will be like this. I'll call it as dF3 vector, dF2 vector. In general, I can call dFi vector. So now all those segments, I can draw the frictional forces by the string and so on. So this will be the figure. Now you can see, for example, this part. Here I can resolve it into horizontal and vertical parts. And this side.
So could you please explain why friction is from left to right direction? Because the string is moving from left to right, so friction should be opposite to it, I think. I have no idea about it.
Okay. So right now I am drawing the string. This dashed curve represents the string. You are correct, ma'am. You are saying string is moving in this direction. Do you agree with this arrow?
Yes, sir.
If it is, that means relative to the pulley. Pulley I am drawing here. Relative to the pulley, it has a tendency to slip in this direction. If I choose this segment on the string first, this part of the string, you are saying on the string friction should be in opposite direction. Do you agree with this?
Yes, I think so.
Yes. If on the string the friction is in opposite direction, who is exerting that frictional force?
Surface of the pulley.
Pulley, yes. So this is the, suppose I write this as dF. So this dF is the frictional force on whom? On the string. By whom? By the pulley.
Yes, sir.
Just apply Newton's third law. What will be its counter reaction? The reaction will be in opposite direction of same
Okay, it is
magnitude.
the reaction force. Okay,
Yes.
okay, I got it.
So actually, who friction on whom? In first part, in the question we are talking the net friction on the pulley, So this dF is the friction on the string and this dF is the friction on the pulley. They will be in opposite direction. Is it okay, ma'am?
Yes, sir. Thank you, sir.
Okay. Okay. Thank you, ma'am. Now we see here. So as I was discussing, over here you see I have resolved the frictional force into two components, and over here now I am resolving. It will have a horizontal component like so and a vertical component like so. This horizontal component, sorry, this vertical component and this vertical component, they tend to cancel. Let me make one statement here. I do not know whether they will cancel exactly, but they tend to nullify each other's effect. But the horizontal component, this part and this part, they tend to add up. And similar will be the condition for other pairs which are symmetrically placed about the pulley. So while it might be possible that the vertical component vanishes or it is negligible, the horizontal component for sure will not vanish because all the frictional forces which we have represented as vectors on this segment, they have a horizontal component and that horizontal component will be towards right.
Right.
So option number D is the correct option in this particular situation. Now my question. If this is the pulley and in horizontal direction, there is a net force on, this is very interesting to find.
Sir,
That,
uh,
yes,
uh, sorry to interrupt, sir. So if it was the question said that friction on the string by the pulley, then the component would be towards the left.
and that the answer will be towards left. Yes, ma'am.
Only in that case. Okay.
Yes,
Thank you,
yes,
sir.
ma'am. Yes, ma'am. So if on the pulley, the net frictional force is towards right. By whom? By the string. But the pulley's center of mass remains at rest. Net force has to be zero. That means there must be some force which is acting towards left. Can you guess who is exerting that force to the left?
Pardon, sir?
Let me repeat my question. Just now we have seen that on the pulley there is net force in the horizontal direction due to friction exerted by the string. So let me represent that by this force vector. But the center of mass of the pulley remains at rest. The pulley turns, no doubt, it is in motion, but its center of mass remains at rest. If its center of mass remains at rest, net force on the pulley must be mass of the pulley times acceleration of center of mass of the pulley. Since center of mass is at rest, its acceleration has to be zero. So net force has to be zero. If net force is zero, net force in horizontal direction must be zero and net force in vertical direction has to be zero. Now, if net force in horizontal direction is zero, One of the horizontal component is the friction towards right, which we have just now discussed. My question is, if friction is to the right, there must be some force to the left that should cancel the friction. Who is exerting that leftward force?
Won't it be the friction
Axle,
by the pulley?
axle on the
Axle.
pulley,
Okay.
on the pulley.
Axle on the
Uh,
pulley.
won't it be the reaction force, sir? Just what you were mentioning, that it will be the frictional force by the pulley on the string.
Friction by the pulley on the string.
By the pulley on the string. So even when the
Madam, please
string
could
is
you repeat
exerting
your
a
question?
no, I'm saying won't it be the reaction force which keeps the center of mass the net force on the center of mass zero?
That is what I'm asking.
So
We'll
so there
discuss
will be a
this in more
reaction
detail.
force. So
Reaction force by
won't it be
whom?
the
By
reaction
whom?
by the pulley on the string? The frictional force by the pulley on string.
See, madam, we are considering the free body diagram of the pulley here. I wish to discuss
Yeah.
equilibrium of the pulley. So when
Yeah.
we wish to discuss equilibrium of the pulley, I should indicate forces on pulley, not the forces
Okay.
by the pulley.
Okay. Okay. Okay.
So on pulley, one of the forces we discussed, it is by string towards right in the horizontal direction. To make it at
Yes.
a rest, there must be some other force by some other agent other than the pulley, which is acting towards left. What is this
Ah,
force I was
understood.
asking?
Okay. Okay. Got the point. Got.
Okay. One of the responses I have received that probably it is by the axle. So the axle is here, and that axle, instead of exerting a vertical force, suppose that axle exerts a tilted force like so. This is the force exerted by the axle. Then it will have a vertical force in upward direction and a horizontal force like so. But I am not sure if it is correct or not. And this will form a part of our discussion in the
Sir,
coming slide.
sir, I have a small doubt regarding this friction force. First of all, when we are moving from left to right over the pulley, since normal reaction force is also increasing as tension is being increased,
Mhm,
therefore, I think friction force is also increasing.
mhm,
The two points which are equidistant with
mhm.
respect to center, I think their vertical component of friction force will not cancel out each other. And
Yes,
probably,
you are
I
right.
think so, there should be a vertical component of the friction force downwards. And
Yes.
that downward friction force will counter by reaction force by the axle.
Mhm. Sir, we are talking about the horizontal part.
Okay. Sorry, sir. I thought no, you just saw wrote there, na, कि vertical component tends to zero. That's why I
Uh,
come.
Sir, here I have written tends to 0, but वहाँ एक caution के साथ I have indicated there that the vertical component may not be 0. It may not cancel completely. But I have skipped
Hmm.
that part.
Okay.
There may be situations where in fact, strictly speaking, friction at different parts on the upper part of the pulley are not same at different sections. At some portions, friction might be more. Again, I will not say are more. At some situations, limiting friction will be more. Here, limiting friction will be more. Here, limiting friction will be less. But here, we are dealing with static friction. We'll see if time permits, we'll come to that particular discussion. Okay, so here I have not answered, and here I have given two clues that the frictional force might not cancel, as Basu sir was saying, the vertical components. But undoubtedly, there has to be a horizontal component by friction. All of you agreed, option number D, friction is a horizontal component to the right, correct. So if it has a horizontal component, there has to be some force which balances it. So some responses I received that the axle should provide component, horizontal component in that direction. To that, again, I, with word of caution, I indicated that we do not know it is correct or not. Let us now proceed further. Let us explore. And we will be happy to see that it will be explored by our own thing. And that is the question now.
Sir, one thing which I'm thinking of, like if the friction on the pulley is towards the right, then as the pulley tries to come towards the right, the right string can exert a reaction force on the,
Mhm.
which may cancel out.
Yes, yes. It's quite logical. It's quite logical. So we are coming to that. So before we come to that normal reaction part, I'll first discuss this the reaction offered by the axle. This was one of the responses. So let me give it a thought. And if R vector be the net reaction vector by the axle on the pulley, then you have to logically think and arrive at a conclusion and specify whether it acts vertically upward, left, or to the right. I'll pause for 2 minutes here, couple of minutes. Please think over it and try to arrive at the answer. Have we started receiving responses?
Sir, are we assuming pulley
Yes,
as
sir.
massless?
No, sir. For all the situations, the pulley has some mass. The situation remains the same. And here M2 is greater than M1.
So there is one query. Is it the normal reaction by string on the pulley?
No. Let R be the net reaction by the axle. Question specifies it. By the axle on the pulley. Axle is connected to the pulley at the center at point O. It is pivoted at point O. Our pulley is heavy, our string, or for all situations, we have assumed our string to be light. And request all the participants to kindly participate in the response giving part. That will help us guide the discussion. Whether it is required for discussion or not, that will help us know. Ma'am, could you please?
Yes, majority have written sir B, and the two participants have written the choice A. Otherwise, all have written B.
I have also written A because my chat box, typing computer is problem. I've given the short sequence for.
So, Tapa madam, could you please repeat what you told?
So she's saying that my choice is also A.
A.
Okay. Okay. So, because most of the options are B, R has horizontal component to the left. Okay. And probably, as far as I can understand, because the net frictional force is to the right, so the reaction by the axle should have a horizontal component to the left, which should balance the frictional force. Probably that is the logic. And that logic seems fine. Nothing wrong in that logic. But let's see another logic. Here in this part, this is the pulley, disc, and on that pulley, we have this string. Now here, pulley plus string, we choose as a system. Now this is one trick we are going to do. So far we were discussing only about the pulley. Now what I wish you to think, pulley and along with that pulley, the upper part of the string also should be included in the system. Now please help me in drawing the free body diagram of this system we have to indicate only external forces, not the internal forces. Which forces should we include?
So weight.
Okay.
एक्सटर्नल फोर्स तो रहेगा, इंटरनल फोर्स इन द ओनली बाय द फ्रिक्शनल फोर्स का जो काउंटर पार्ट आपका रिएक्शन मिल रहा है उसको तो इंटरनल बोलेंगे ना हम लोग।
Yes.
वो तो रहेगा ही तो।
My system is pulley plus string. So pulley's force on the string, string's force on the pulley, they will be internal forces. So we need not indicate such forces in the free body diagram now. So we will get rid of those frictional forces and normal reactions. So as sir told, there will be a weight. Whose weight? Weight of the pulley. I represent it as WP. What else?
Sir, can
Normal
I add
reaction in the
something?
upward direction in case of rest.
Madam, please
Normal
repeat.
reaction in the upward direction
Okay.
if the system is in rest.
See, our task is to find the direction of normal reaction or the net reaction, not normal reaction, the net reaction vector by the axle on the pulley. So I would like to draw that at the last. Let us see first the other forces.
Sir, can I
Somebody was
add
willing
something?
to add something.
Yeah, sir, actually, I was thinking like if there is axle in the center of the pulley, it is passing. So generally, it would not have much room into it. So the only case that is left with that axle can exert an upward normal reaction on the pulley. That what I was thinking of initially.
Okay. But there are some other forces also other than the reaction by the axle and gravity, that is WP. There are other forces. You are missing some part.
Which can exert reaction on pulley.
No. So any force on this system, our system I have specified. On this system, I wish to list all the forces. One force is WP.
That
Other force, as you were saying, reaction. What else?
Friction between pulley and the axle.
Friction between pulley and axle. Yes, very nice. Friction between pulley and axle is there, but we will be treating such cases where such friction between. Now I will pause a bit and clarify here. Friction between pulley and axle is 0. And such situations we specify in the question by saying that the pulley is smooth. Now let me deviate from my discussion right now because very interesting point madam has raised. In numericals or in situations, often it is written the pulley is light and smooth. When we say the pulley is smooth, it is smooth where it is connected to the axle. Here the friction is 0. But where it connects to the string, this upper part, this part, where it is connected to the string, here it is not smooth. Because here if it remains smooth, then the pulley cannot turn. So for the pulley to turn, there has to be friction between the string and the pulley. So off topic, whenever we say that the pulley is smooth, it means the axle exerts 0 friction at the center where it is pivoting the pulley. But string exerts a frictional force on the pulley because of which the pulley turns in some direction. So madam, we will assume that there is no frictional force between the pulley and the axle. What else?
Weight of M2 and M1 can
What
be
about
taken.
these parts of the string? Weight of M2 and M1 will be acting on the string. But that is not my system. My system is this pulley and this string. Means the string
The weight of the pulley is taken
contact
into
will
consideration.
concentrate on end A.
Then why not M1 and M2?
Yes. Okay. So M1 is here. Its weight is M1G. And this mass M1, actually, is it in contact with this pulley or this part of the string AC, part ABC?
No, there is no touch, but here it is due to the weight M1, there will be tension at the point A, and which is
Yes,
going keep on
yes,
increasing towards
yes,
C.
yes. So, what is the correct representation? Should I say that the force on this system at point A, force at point A is TA? Can I say that?
Right,
But the TA is not equal to M1G, mind it.
right, 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 right.
So M1G is causing some tension in the string. That tension will cause some force at point A. Likewise, at point C, this part of this string, which is held by mass M2, will cause some tension. That tension will also be like so, Tc. This completes our free body diagram of the pulley plus the upper part of the string system. Now let us analyze these forces. One force is missing. One force is missing.
So
I have
TC,
represented three forces.
so TC is then must be more than TA.
Of
So
course.
then we will resolve and we'll get the component towards. Okay, that is why the component to the left. ठीक. Okay, right, sir.
But madam, TC is vertically downward.
But
Weight
you
of
have
pulley is vertically downward. And tension
and
at point A. All these
it
three
is
forces are vertically downward.
but you've done what? So counter force is acting where? To keep it in the balance in the rest of the equilibrium.
So one more force must be there. One more force must be there. And that must be vertically upward. Who can exert that vertically upward force? There is only one possibility, the axle.
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 And that will write as reaction.
Oh.
Before this slide, earlier what we were discussing, it was there in our mind, probably this reaction may be tilted. And it will have a horizontal component and it will have a vertical component. And this horizontal component will balance the frictional force. That is what we might be thinking, but that is not correct. I have justified the fact.
Sorry to interrupt. Why the directions of tensions are taken downward here? Weight is downward already.
Now, tension on whom? At which point? If you consider tension at the lowest point, that tension will be in upward direction. Tension always pulls. It cannot push. So we are not discussing the tension at the lowest part of the string. We are discussing the tension at that point of the string, which is near point A and point C. By whom? By remaining part of this string. This lower part of this string at the left end as well as at the right end, they can only pull the point A. They cannot push point A. Imagine tying a mass to a string and we can pull that string and accelerate the mass. But by pushing the string, we cannot accelerate the mass. The string will become loose. So here, that's why on the left side as well as the right side, hanging portions of the string, they will be pulling points A and C, and that's why the tensions will be in downward direction at points A and C, represented by TA and TC. So the correct answer to this part, question number 4, should be option number A. R strictly acts vertically upward. It has no horizontal component. It has no horizontal component to the left or to the right. It is only vertical. So let us now proceed to the next slide.
Sir, is it right to
Yes,
say
sir.
that axle and pulley are made in such a way, even if there is something which tries to pull it leftward?
Sorry, sir. Please repeat, sir.
Sir, is it right to say that axle and pulley system is made in such a way that even if some agent is trying to put the right side or left side, it wouldn't? The net reaction should always be upward.
So let me, because you have raised this question, I leave it to as a task. I am drawing two situations. If the
So in that
hanging part
case,
of the
what
string,
balances the friction in this case? What balance
Madam,
creates a horizontal equilibrium here?
that forms my next part of discussion, ma'am.
Okay.
Okay. I'm responding to Manish sir query. Sir, I'm just giving without any justification. Justification for the first part I have already given. If the hanging parts of the string are vertical, then the reaction has to be vertical. But if the hanging parts, not hanging parts, if suppose the strings are like so, making some angle with the vertical, in that case, this tension will be different. Let me take some time, T1 and T2. And then in that case, the reaction may not be vertical. T1 will have components, horizontal and vertical. T2 will have components, vertical and horizontal. In horizontal component of T2, which I write as T2H, because T1 is greater than T2, T1H will be greater than T2H. So now there will be resultant force towards right. So to counterbalance, the reaction force will now not be only vertical, it has to have a horizontal component to the left. And then the reaction force will be tilted like so. And it will have a component in vertical direction and in horizontal direction, which will balance the forces when
But sir,
taken
in that
together.
situation, sir, in that situation, in practical way, we see that pulley system wouldn't work.
In which situation?
The situation that in second situation that you have taken, where tensions are at angle.
Just you ask a person to hold it at some angle. Ask another person at T2 to hold it at some angle. Ask them to pull the string. They will pull with different forces. String will have different tensions, just as we have discussed, and then the situation will arise. We are discussing only those situations where the masses are hanging vertically downward and the parts of the hanging portions of the string are vertical. In such situations, as I discussed just in this slide, the total reaction by the axle on the pulley has to be vertical because there is no other force in the horizontal direction. So the reaction of the axle also cannot be having a horizontal component.
Okay, sir.
Ma'am, you asked some question that will be covered in this segment. That is, this question is the clue to your query. Let the normal reaction be n vector, and this normal reaction is by the string on the pulley. Now we have to decide whether n acts vertically downward, or it has a component to the left, or it has component to the right. Let me summarize here that m2 is greater than m1. My string is light. My pulley is heavy. And what we have discussed so far that the reaction by the axle on the pulley has to be in upward direction. And we have discussed earlier that the net frictional force has a horizontal component towards right. Based on these arguments, try to answer question 3 on the screen. I'll take a pause for a couple of minutes. I will be waiting for your responses. Normal reaction vector by the string on the pulley.
So what is this small f?
So that we have discussed earlier, friction, net frictional force by the string on the pulley. We have discussed earlier, it is towards right.
Okay, sir. Sir, when we discuss the friction, does the friction force was increasing from A to B and then B to C?
That we have not discussed. But let me show you that slide if you wish. Oh, but then question will be omitted. We'll discuss that, sir. Here we are just willing to find the direction. So we should not bother much about the magnitude.
So again, for me, it's A is coming in my mind. Because
Okay.
Ma'am, could you tell what are the most of the responses?
Sir, number one is B, and one has written C, and E. One has she had said E. So this is main is B, and then second is
Okay.
yes. Main is
Now,
B.
before discussing the okay.
Yes.
So I think most of you have responded based on what we have discussed so far. So the pulley's free body diagram so far, whatever we have discussed. So the string, the reaction force by the axle, we have discussed it is in upward direction. Weight of the pulley, no doubt, no uncertainty, it must be in downward direction. Now the string which is wrapped around that pulley, it exerts two types of forces. One is normal reaction, which will be at different segments in different directions. For example, here the normal reaction will be like so, here it will be like so, here it will be like so, then like this. And the frictional force by the string on the pulley we have discussed earlier, that will be tangential, like this. And because of tangential nature of the frictional force, it will have components. The vertical components will not or may not nullify completely, but the horizontal components will be in this direction, in both the sides. So the net frictional force by the string on the pulley has to be towards right. Now to make it balanced, there has to be some force. See, R and mg or WP or the vertical component of friction, those things can balance. But to balance this F, we don't have anything left. So it has to be N. There must be some force to the left, and that leftward force who can exert? The normal reaction which is exerted by the string is the only possibility. So this diagram which I'm going to draw, this is not the correct representation of the force representing the normal reaction by the string on the pulley. What the normal reaction has to do, it will tilt like so. And it will have a vertical component and it will have a horizontal component.
horizontal component.
That horizontal component of normal reaction will be able to balance the frictional force.
Friction force.
So that's why option number B is correct. Now coming to the query which was raised by Basu sir, this suggests that the right part of the string, it presses harder on the pulley when it rolls in this direction compared to the left part of the string. It presses less harder. If I divide this symmetrically into two halves, the left half and the right part of the string in the right half presses it harder. That means this force I should represent with a longer arrow, n to the right, and this will be less, nl. So when we resolve them, the vertical components will add in downward direction, but the horizontal components don't cancel completely. The horizontal component of nr and the horizontal component of nl, they are not having same magnitude, but they are in opposite directions, so they do not cancel. This results in net horizontal component of normal reaction, and that's why it acts towards left. So if I draw now complete free body diagram of the pulley, only the pulley. So its free body diagram based on today's discussion is this. We will assume all the forces to be acting through the center of mass. So weight of the pulley in downward direction, reaction by the axle in upward direction, frictional force dominating horizontal component will be towards right. This is the horizontal component of frictional force. There might be some vertical component of frictional force, might be FV, and the normal reaction will be tilted like so in this direction.
Here is a big query. NV is when you're resolving N, that is up to till I am clear, because that is why I have written NX vertically downward. When you're resolving, NH and NV will be not equally, because then NH is counterparting with the frictional force. What about NV? NV should not be it should be equal to the NH with the because you're resolving the component angle if it is a 45 degree. That is my question. Is that means it is not 45?
Madam, wait, let me translate your version in form of a figure.
Thank you, sir.
And please help me in what you are saying. First, I should choose two symmetrical points over here and over here.
Right.
Right? And here, normal reaction, I am writing it as suppose NR.
NR, yes.
And here, normal reaction, I am writing as NL.
Towards the center, yes, NR.
Towards the center. My argument was that NR and NL will not be having same magnitude. It must
because
be
the
NR
mass,
than NL.
because the masses are different. Yeah, right.
What next, ma'am?
The thing now you are resolving the normal reactions at the point right hand side. M2 is
So
acting.
let me call this as NR horizontal, NRH.
Right.
And this I write as NR vertical component, V.
Oh, but right.
Likewise here, NLH.
Right.
And this one NLV vertical
Right.
component.
So
Okay.
you are balancing at the right hand side, but NRH, the frictional force, here also you are doing the frictional force counterpart balance. So what about the NRV? NRV is components is working in the two different, because NRH, NRV and NLH V is not same. Normal reaction work.
NRV is in downward direction.
Right, and NRH also in the NLH is also V also in the downward direction.
Not
this
NLH,
point.
NLV.
NLV, yes, left wala,
Is
yes.
in downward direction. That means when we talk of the entire pulley, there has to be net downward force of the normal reaction.
Right.
And there has to be, now you see, and this net force will be sum of them, NLV plus NRV. Because their directions are same.
Same. That is why I have said to the component इसका नीचे ऊपर counterpart नहीं लेंगे ना, इसका totally
I'm just coming to that, madam. And the horizontal components, one is NLV, one is NRH. They are not equal. NRH is greater, NLH is smaller, so they will cancel to some extent. The resultant will be NRH minus NLH. Okay. Now their resultant.
It is also
the total normal reaction should be like so.
Like so. That is why I'm telling.
This is N. And this is not vertical, this is not horizontal, it is inclined.
Right.
And if you see, ma'am, this is the same thing which is being translated here in this figure. The N in this figure on the pulley is inclined.
Inclined, right.
This is the total normal reaction.
Right.
Now we have four forces on the pulley. One is normal reaction. This is number one. One is weight. This is number two. One is the frictional force. Now frictional force is also inclined, actually.
Inclined. Okay. Got it.
Frictional force also has to be inclined. whose horizontal component I have represented as FH and vertical
हाँ
component I have represented as FV.
FB.
So now I'm removing F. Instead of F, I have written as FH and FV. And likewise, I will remove N and I'll replace N with NV and NH, the
Okay.
components.
Hmm.
Normal reaction I'll resolve into horizontal and
Hmm.
vertical components. So
Right.
its horizontal component I'll write as NH and
Hmm.
vertical component I'll write as NV. Now
So,
in horizontal direction, let us see all the forces. In the right
hmm.
direction, I have FH and in the left
Hmm.
direction, I have NH. So I must
Right.
have F is equal to NH.
Right.
That means in horizontal direction, the friction by the string and the normal reaction
Hmm.
by the string, they cancel each other.
Hmm.
It's number one. And in
Okay.
vertical direction, the upward forces are R and FV, vertical component of friction. And
Okay.
downward direction, we have weight of the pulley
W
plus
plus NB.
NV. NV. This is NV.
हाँ.
They will balance in the vertical direction. And that's why the pulley's center of mass will remain at rest throughout the motion. So in the
That means,
horizontal
sir,
direction, net force is
as
zero.
uh-huh.
Yes, ma'am.
So W and R is equal. We have seen in the last numerical. So FV must be equal to NV to keep this N as horizontal component to the left. Am I
Okay.
clear?
In the last example where I've written W and R are equal, there we have to understand what is W. It is the weight of the pulley.
Hmm.
And here, what was our system? Our system was not the pulley. Our system was here I've written pulley plus string.
Okay, right. Thank you, sir.
Here our system was pulley plus string.
And string. Here it is inside the pulley.
Here it is only pulley. So
Oh.
that change will be there. So here the normal, the reaction R by the axle plus vertical component of friction will be equal to weight of the pulley plus normal reaction of the string. Now here NV and NH, this NV and NH, this is by the string on the pulley. But in the earlier case, this was internal force, so we have not included N in our discussion there. But here our pulley is the object being discussed, so N has to be included because it is external force in this case. Is it okay, ma'am?
Thank you, sir, very much.
Now I'd like to conclude. We have last 15 minutes. Conclude this topic.
So one last
With interesting part.
query, sir. What justification we can give that the normal reaction on the right side is more as compared to left? Is it friction or tension?
See, there are tension on the right side. Tension on the right side is more compared to tension on the left side. This we have discussed earlier because tension is gradually increasing. That is one part. When tension is more, just let me try to draw a figure here. If I choose this segment, here it is being pulled tangentially. Here it is being pulled tangentially. This is T1, suppose this is T2. And identical segment, if I choose this side, tangentially this side, tangentially this side, they are being pulled. In the right side, the tension in the string is more. T1 and T2 are comparatively more than T3 and T4. If tensions are more, now when we try to resolve, here this is the normal reaction which I am writing as N. Let me write it as NR. If I resolve T1, I'll get a component of T1 in this direction, then I'll get a component in this direction, something like that. So these components of tension on the ring will be counterbalanced by NR. Since these tensions are more, so this NR has to be more compared to the similar argument we can give for NL. On the left side, since tensions are small, the normal reactions involved there is also small. In the right side, since the tensions are more, normal reaction will be more. That is one justification. Another justification which you can give, sir, earlier we had discussed that the net horizontal component of the frictional force is to the right. And some amongst you was saying, if the pulley tends to move towards right, then which of the two strings, one or two, will press harder against the pulley? String 1 or string 2?
So 2.
String 2.
2.
If string 2 presses harder against the right side of the pulley, we can expect the normal reaction at the right side to be greater compared to the normal reaction to the left side. You can give different lines of reasoning.
Yes, sir.
So, I will not be able to complete the other question. So we'll confine our discussion to pulley only. Now, torque equation of the pulley, what we write? Suppose the tension here. Suppose the tension at point C is T2 and tension at point A is T1 and the radius of the pulley is R. And moment of inertia of the pulley is I. Then the equation which we write is this. T2 minus T1 whole into R. This is a very common relation. Is equal to I times alpha, where alpha is the angular acceleration of this massive pulley and I is the moment of inertia of the pulley. My question, my submission is that when in the free body diagram, we are not including T1 and T2 as discussed earlier, why do we write? Because this equation, if you assume, actually what we do, we draw the free body diagram like this. We draw here T1, we draw here T2. That's it. And then we say the torque is T2 minus T1 in T2 into R minus T1 into R, and net torque is equal to I into alpha. But just now we had a discussion that these forces are not to be included in the free body diagram of the pulley. If they are not to be included, why should we write T2 minus T1 into R is equal to I into alpha? That is what I am going to discuss. So for that, consider this segment of the pulley and the string. Let me first discuss about the string. This string is light. If the string is light, I will divide it into different
But is it
segments.
because we consider the string, the upper part of the string and pulley as one system, like we did
Yes,
earlier?
yes. No, we do not
So
consider.
that
We do not consider. But if we consider the upper part of the string, which is light, plus the pulley as a system, together it will give the relation T2 minus T1 R is equal to I alpha. An excellent point. But generally, we write it as a free body diagram of the pulley, and then we write this equation. What madam told, if we consider pulley plus string as the system, then yes, this is T2, this is T1, and then we can write T2 minus T1 into R is equal to I alpha. Excellent point. But my take is if I consider only the pulley, can we arrive at the same result or not? For that, let me first talk about the string. On this string, I have divided it into different segments. And as discussed earlier, on this segment, the frictional force is like so. I'll call it as dF1 vector. Likewise here, dF2 vector. In general, suppose this is dFi vector, ith segment, and dFn vector, likewise. And the normal reaction, likewise, this I'll write as dN1 vector, this I'll write as dN2 vector, and likewise the ith segment, I'll write it as dNi vector. These are the forces on the string. No other forces are there on the string. And this is the center. So let us write the torque equation for this string. For string, what we can write? Net torque is equal to I into alpha. Whose I? Strings I. Whose alpha? Strings alpha. But string is light, so moment of inertia has to be 0. Now please help me in writing the net torque. Can you tell me which of the two forces, the frictional force or the normal reaction on the string, will provide torque about point O? We are finding torque about point O. Who will provide the torque, the friction or the normal reaction? Friction. Because the normal reaction, all those normal reactions, they are passing through O. All the normal reactions will pass through O. So the torque due to normal reactions will be 0. So the only torques will be dF1 vector. Now, this force dF1 vector, how much will be the torque? Torque will be that force multiplied by perpendicular distance from O, which is equal to radius, so R, plus dF2 vector, not vector, it's magnitude, into R, plus dF3 vector into R, magnitude of dF3 vector, and so on. This net torque, as discussed earlier, has to be 0. So this I can write as summation of dFi into R Acha. We have committed one mistake here. We have left some forces here. On this string, two more forces are to be indicated. The left part is A, the right part is C. Sorry to miss those points. At A, this string is being pulled downward by a force TA. At C, this string is being pulled down by a force that is TC. So two more forces will come here. One will be TC into R and one will be TA into R. But if you see carefully, TC tends to turn the string in this direction, and TA and all other frictional forces tend to turn the string in the other direction. So their torques are in opposite sense. So TA's torque, if I take as positive, TC's torque has to be negative, and this total has to be 0. So this frictional torque, I have written as summation dFi into R, plus again from these two part I can take R common. So TA minus TC into R is equal to 0. R you can take common and send that side. I'll get the summation of dFi. That means this is the total frictional forces. Sum of the magnitudes of the frictional forces is equal to TC minus TA. Let me call this as equation number 1. This relation we have arrived based on discussion on the free body diagram of the string. Now the same thing we'll do for the pulley. With one change, that if on the string the normal reactions were towards O, on the pulley the normal reactions will be away from O. If I consider different segments, here the normal reaction will be like so, here normal reaction will be like so, and so on. Let me call it as D and I. And the frictional force on the string and the frictional force on the pulley, they will also be in opposite direction. Similar reasoning, dFi. dF1, dFi, dF2, dF3, and so on. The frictional force will be tangential. On the pulley, the only force by the string are the normal reaction and frictional forces. Other than that, there is weight of the pulley and there is reaction offered by the axle in upward direction. Again, let me write the equation for this. Net torque about point O is equal to I of the pulley times alpha of the pulley. Now net torque about point O, again as we discussed earlier, W and R and D and I, all of them they pass through O, their torques will be 0. Only agent that will provide the torque is the frictional force. So dFi times R. Likewise, dF1 into R, dF2 into R, dF3 into R. So net torque will be summation dFi into R, and that will be equal to I of the pulley times alpha of the pulley.
So once
Now
more,
I will take help of
sir,
equation 1. Which part?
sir,
Which part?
once more, पुली के ऊपर क्या क्या फोर्स लगा रहे हो खाली इसको थोड़ा सा
Okay, ma'am. Okay, ma'am. On pulley, there are four forces. Four forces. Force number one is weight, no doubt about that. Force number two is reaction by the axle. Both these two forces, weight and R, they pass through the center O of the pulley. So its torque will be zero and the reaction's torque will also be zero. Now two more forces are left. One is frictional force, like this, dF1. Then here I have written dFi. This is dF3, dF4, dF5. Different segments will have friction because of the
different.
string.
Mhm,
And on those segments, the string will offer reaction.
mhm,
This is dN1, dN2, dN3. One segment I've chosen here. On that segment, the reaction is dNi and the frictional force is dFi. But reaction force also passes through O, so this will also produce zero torque. Only agent that will produce torque is the frictional force. Now the total torque, how will we find? Total torque will be sum of all the frictional torques. So dF1 into, now this frictional force is its perpendicular distance from O is equal to radius of the pulley. So dF1 into R plus dF2 into R and so on. Likewise, we have to add all of them. And this will be equal to the right hand side, that is I times alpha. So this I can write as summation of all the frictional components. So dFi into R is equal to I into alpha. Now this part you see. This part we have already used up here. Summation of dFi in equation 1 is nothing but Tc minus Ta. So this I will substitute here, and instead of summation dFi, I'll write Tc minus Ta whole into R equals to I times alpha. And this is the relation which we write for the pulley, but probably we miss this part that we are not considering the forces only on the pulley, but as one ma'am suggested, if we consider pulley plus string as the system, then we can easily arrive without doing so many, without worrying about the frictional forces, the normal reactions, we can directly write Tc minus Ta into R is equal to I times alpha. So there are things left in my today's
Sir,
planning,
uh,
but I will stop here. Let me see. Yes, this part I will skip because that will cover more time. So I'll stop here. So let me first briefly summarize in today's discussion what we have discussed so far.
sir,
That
sorry,
we-
sir. I have one doubt here.
Okay, sir.
Sir, these the string talks. How you made it zero, sir? I just missed that because of internet connection.
Nothing, sir. Nothing. String torque is equal to I alpha.
Yes, sir.
That torque on string is I of string into alpha of string.
Okay, sir.
Now we are considering massless string. If it
Yes,
is
sir.
massless, I has to be zero.
Okay, sir.
Now somebody might ask, what is the purpose of this discussion? Actually, all the numericals, we are assuming the string to be massless. And that's why our assumption comes out to be true, T2 minus T1 into R is equal to I alpha. But if the string happens to be heavy, then the treatment which we have discussed here, that will hold true. The method will be like so. So let me briefly mention the key takeaways.
So one more question, please. So you have
Please, ma'am.
taken TC and TA equal here.
No, not at all.
Then
TC is
minus
greater than TA.
TC dot R plus TA dot R is zero. How, sir?
No.
It's not zero. It's not zero.
This is in continuation with this, madam. Please read from here. Before minus TC, it is here. This entire relation. Let me give
Okay,
that part
sir.
again.
Okay. I got it. Thank you, sir.
That minus TCR plus TAR is in continuation with the frictional torques, dFi into R. So the basic takeaways of today's pulley discussion was that in the case of pulley, the first figure which I would like to show here. The string exerts two types of forces on the pulley. One is the frictional force, one is the normal reaction. The frictional force has a dominating horizontal component and a small vertical component. That is one takeaway. The normal reaction by the string on the pulley is not vertical, it is tilted like so. And its horizontal component balances the horizontal component of frictional forces. These are the two important takeaways of today's discussion. Now I thank all the participants for interesting discussion, and I take this opportunity to really accept one fact that both yesterday as well as today it was highly interactive, that made me feel that yes, really people are listening and they're enjoying. I too enjoyed the things a lot, and I thank once again the IPT team to give me this opportunity. I'm sorry, I feel as if I feel as if I should continue more because there are many things which are left. But at the same time, I do understand people are tired. I am also tired. Presenting before you is my problem. Listening to me is your problem. Completing home's task is everybody's problem. So, but if it is everybody's problem, it is nobody's problem. So, with this note, I once again thank one and all, and I hope these discussions will bring some positive change in our understanding and in our thoughts understanding. Particularly, it should be reflected in the minds of the students. With this hope, I conclude my session. Thank you, everybody.
Thank you so
Thank
much.
you, sir. Thank you, sir.
Really appreciate. Thank you.
Very
Thank you, sir.
insightful discussion. Thanks, Jeevan Pandey, sir, for thought-provoking interactive session, including systems involving masses connected by a pulley. A careful analysis of free body diagram of both the pulley and the string has been done. Tensions in different segments of the string, weight of the pulley, and reaction forces at the axle are discussed. A particularly interesting aspect arises when the string is assumed to be light and inextensible. Free body diagram of different situations of pulley string system have been discussed. Finally, torque equations for the pulley have been discussed thoroughly. So my sincere thanks to resource person of today's session, Mr. Jeevan Pandey, for sparing time from his busy schedule. Heartfelt thanks to all the participants for their enthusiastic participation and active discussion. Tomorrow we will have expert talk of Mr. Basu Sahu. So please all must attend. No doubt today, tomorrow is Sunday, but I expect that all the participants will will enthusiastically participate in tomorrow's session. So now my request to worthy members that assignments will be shared in Google Classroom. Please submit classroom these assignments in stipulated time. Please fill your feedback form daily. So thank you. Thanks to all. Thanks to Mr. Sahu Basu, Pragya ma'am, and all the participants. Thanks a lot.